All right, let's jump right into this explainer. Today, we're playing detective on what is arguably an electric vehicle powertrain's most complex failure mode, motor phase current imbalance. If you've spent any time at all around high-performance permanent magnet synchronous motors, you already know this is a totally critical failure. It directly impacts field-oriented control decoupling and ruins the overall system's thermal stability. So today, we're going to break down the highly sophisticated technical specifications, the diagnostics, and the prevention controls that keep these motors running safely. At its core, an electric motor absolutely relies on perfect electromagnetic symmetry. But what happens when that perfect symmetry breaks down? We're going to explore how something as small as a tiny temperature drift in a sensor or even microscopic fretting wear on a terminal can completely shatter this balance. When it happens, it essentially acts like a disease that compromises the entire closed-loop control system, creating these nasty parasitic forces that can actually destroy the motor from the inside out. Here is our clinical roadmap for today. We'll start with root cause physics, move into hardware and software co-diagnostics, upstream DFMA prevention, factory floor PFMEA process controls, and finally wrap up with DVP and R validation.
Let's kick things off with Section 1, Root Cause Analysis, focusing on the physical breakdown of motor asymmetry. Sometimes the motor is actually perfectly fine, but the dual motor controller literally hallucinates a problem. We call this a false imbalance. It's a fatal misreading where perfectly symmetric currents suddenly appear asymmetric to the system. Why does this happen? Well, think about the environment. The system is operating in extreme temperature shifts, often bouncing all the way from -40 to 125 degrees Celsius. These intense thermal cycles can actually warp the current sensor's magnetic core, degrade the amplifier gain, and age the analog front-end filter capacitors, which completely distorts the baseline data.
But beyond those sensor hallucinations, we have very real physical threats out there. The first is stator and rotor impedance asymmetry. Imagine severe vehicle vibration causing microscopic fretting wear on the wire harness terminals, which can spike the contact resistance from under 5 milliohms to a critical level. Or you could have electrodischarge machining, or EDM, wearing down the bearings and causing a dynamic runout of greater than 0.05 millimeters. That literally warps the air gap magnetic reluctance. Then you've got switching and dead time asymmetry. These are microscopic delays in the silicon carbide or IGBT logic gates that misalign the voltage vectors. And finally, angle estimation errors. If the rotor position sensor lags even a little, it causes DQ axis coupling. The direct axis, which should be 0, suddenly generates parasitic currents that actively demagnetize the permanent magnets.
Moving right along to Section 2, hardware and software co-diagnostics. This is basically the system's ultra-fast immune response. 1 single microsecond. That's how fast the hardware reflexes. Every single phase current sensor has an independent overcurrent detection pin routed directly to the main microcontroller. If that analog voltage overflows, the system can completely lock out the pulse width modulation in just 1 microsecond. It is an absolute hard stop, meant to prevent an instantaneous, catastrophic failure. Now, to cure that false imbalance hallucination we talked about earlier, the software runs an automatic zero-offset calibration. During cold starts, when absolutely zero current is flowing through the three-phase bridge, the system runs the analog signals through a low-pass filter. It converts them into a high-precision Q15 data format, dynamically calculating a baseline with 4-digit precision. This perfectly erases any thermal zero drift before the motor even turns on. And that hardware reflex is backed up by continuous software protection. While you drive, the software runs intense background diagnostics. Step 1 is a Kirchhoff's current law residual check. It's constantly adding the three-phase currents together, and if they don't perfectly equal 0, it spots a physical leak gauge or sensor mismatch in under 2 milliseconds. Step 2 is negative sequence extraction. The software actually decouples the fundamental current to isolate the negative sequence, which represents electrical asymmetry. If this ratio breaches a 5% threshold for more than 3 milliseconds, an alarm triggers. Finally, Step 3 dynamically compares AC terminal power with high-voltage DC bus power to quickly isolate any random gap failures. But if a severe physical imbalance is confirmed by those software layers, the system is officially on the clock. It has to act within a strict functional safety fault-tolerant time interval, or FTTI, of just 60 milliseconds. If it fails to act within that incredibly tight window, you are looking at guaranteed avalanche breakdown, where the immense demagnetization currents will literally melt the power modules.
To prevent that total meltdown, the controller deploys a staged, highly calculated fallback response. If it's just a mild imbalance, say between 5 and 15%, it gracefully degrades into a Limp-Home mode. Using PI regulators, it smoothly drops torque to 30% and limits the car's speed to 40 kilometers per hour to minimize thermal stress. But if it's a severe imbalance of over 20%, there's no messing around. The system immediately locks the gates and triggers a stepwise active short circuit, forcing the motor into a safe state entirely within that 60 millisecond window. Next up is Section 3, DFMEA, Key Design Prevention. Think of this as doing some genetic editing right on the design board.
How do we vaccinate the system before it's even built? Well, first rule, we completely ban thermally unstable Class 2 X7R capacitors in the analog front-end circuits. They are just way too prone to high-voltage thermal drift and piezoelectric aging. Instead, the design strictly requires rock-solid Class 1 COG or NP0 ceramic materials paired with 0.1% precision low-drift film resistors. This is absolutely crucial to guarantee analog sampling perfection and a high common mode rejection ratio.
To compensate for unavoidable physical limitations, the controller design also incorporates dynamic 2D inductance lookup tables. Because inductance actually changes based on real-time current, these nonlinear tables digitally correct magnetic cross-saturation on the fly. Paired with feed-forward phase compensation, it instantly offsets group delays from the filters, keeping the stator magnetic field perfectly aligned and preventing those dangerous angle estimation errors.
Finally, physical symmetry in the mechanical layout is strictly enforced. The high-voltage three-phase bus bars must have perfectly symmetric spatial geometries. The dynamic power cables literally have to be identical in physical length. Self-inductance, mutual inductance, and leakage impedance mismatch are all ruthlessly capped at below 2%. This pretty much eliminates any chance of physical space asymmetry triggering high-frequency differential mode imbalances.
Let's move to Section 4, PFMEA, Key Process Controls. This is where we vaccinate the system right on the factory floor. To actually achieve that physical perfection, the assembly line operates like a highly sterile lab. It starts with end-of-line calibration. The system injects precise AC reference currents at both high and room temperatures to calculate dynamic gain and zero bias, flashing that directly into the EEPRM memory. Then we use high-precision servo screwdrivers utilizing a torque angle method on phosphate-coated bolts, guaranteeing the exact axial preload to prevent that dreaded fretting wear. And to finish it off, a high-sensitivity helium leak test assures a leak rate of less than 10 to the -5 millibars liter per second. This completely stops moisture and oil from ever causing electrochemical migration. Finally, Section 5, DVPNR validation. After all that design and control, this is the ultimate laboratory stress test to prove it works. Just look at some of the extreme criteria on this validation table. For dynamic current balance, the motor and controller are violently vibrated at 35 meters per second squared, all while rapidly cycling between -40 and 125 degrees Celsius for over 500 hours. The pass criteria? Phase current imbalance must stay below 3%, and contact resistance cannot increase by more than 1.2 milliohms. Plus, in hardware-in-the-loop fault injection testing, while the motor is spinning at a blistering 12,000 RPM, engineers actively inject stator shorts. The system literally has to diagnose the fault inside that 60 millisecond window, safely triggering the active short circuit while keeping peak voltage below 720 volts and current below 550 amps. It is an incredibly high bar. So, this deep dive really goes to show that functional safety in high-performance EVs is a masterful, multi-layered discipline of physics, hardware, software, and manufacturing. But looking at these stringent requirements and razor-thin tolerances, it leaves us with one critical question to close out this explainer. Are your own systems truly this resilient? And are your diagnostic algorithms really prepared to handle real-world impedance degradation before it completely destroys the motor? Thank you so much for joining me, and keep questioning the perfect symmetry.